Hi, I'm Katherine Song. This is a presentation of our paper, VIM, Customizable Decomposable Electrical Energy Storage. The word VIM means vigor, energy, or go. This is the name that we give to the electrical energy storage elements that we have developed and will describe in this talk. Our motivations for VIMs are twofold. First, providing electrical power is essential for nearly all interactive technologies, yet it often remains an afterthought in the design and prototyping processes. Power conventionally comes in the form of rigid batteries, which come in set sizes and geometries. When integrating batteries into small, low-power and temporary electronics designs, it is not uncommon to find that the design must physically expand to account for and enclose batteries that outsize the rest of the system, both in terms of physical footprint and electronic capabilities. With VIMs, we propose that instead of leaving power as an exercise for later, we elevate it to be a first-class design element that can be developed alongside and iterated upon with the rest of the components of an interactive system. Secondly, conventional batteries present a serious sustainability problem and are some of the most environmentally hazardous components of electronic interactive systems. They rely on toxic metals such as cadmium, lead, or lithium that are extracted through resource-intensive processes and must be carefully contained at end of life. Lithium-ion batteries that are improperly disposed of in regular landfills can cause fires, endangering nearby communities. The lack of sustainable energy storage alternatives is a substantial obstacle in the path of the collective efforts among the HCI community of makers to create eco-friendly interactive systems. There are several noteworthy approaches that we draw inspiration from in thinking about how to reduce electronic waste and design more sustainable energy storage solutions. For example, researchers have created self-sustaining and battery-free systems that can be powered wirelessly through inductive chargers, NFC, ultrasound, and even ambient backscatter from electromagnetic energy from TV signals, Wi-Fi, Bluetooth, and radio, for example. VIMs add yet another approach to this increasingly rich pool of techniques and are especially attractive for temporary applications that cannot be powered from ambient energy harvested from the environment. Now I will discuss how we design VIMs. VIMs are, in essence, supercapacitor structures that can be made from a variety of household-safe and even edible materials. A supercapacitor can be made using just 3 different types of materials. First, a very conductive current collector. Second, a conductive but porous electrode. And finally, an electrolyte with mobile ions. For our exemplar VIMs, we use graphite as a current collector, activated charcoal bound with CMC and water as an electrode, and table salt, glycerin, and CMC as an electrolyte. The fabrication of VIMs takes minutes and is done with entirely DIY-friendly methods and safe materials. First, an electrode ink is mixed by combining activated charcoal, CMC, and water. Next, an electrolyte composed of glycerin, salt, and CMC is mixed. The electrode ink is then screen printed onto a conductive current collector, such as graphite foil. After drying, the electrolyte is barcoded onto the electrode and then dried again. VIMs are completed by then cutting the prepared pieces and pressing them into a sandwich. VIMs may be shaped, reshaped, and cut into different geometries, and by using different materials, such as edible gold leaf instead of graphite, we can also achieve different aesthetics that can be customized to the application. Under a constant voltage charging scheme, VIMs can be charged to 2 volts within 5 minutes. VIMs may be more quickly charged by using a constant current charging scheme with higher current. Under a charging current of 100 milliamps, a VIM reaches 2 volts in just 5 seconds. Thanks to their flexibility to charge under varying current, VIMs can also directly be connected to solar panels or other energy harvesters without the need for a charge regulator. A single VIM can readily power small electronic components like LEDs. By chaining 4 VIMs in series, we can create storage elements that can be charged to 10 volts in 3 minutes and can power a 3.3 volt device for over 24 hours. VIMs can double as decorative elements and a power source, powering some electronics like this clock for an entire day. After fabrication, VIMS may be bent, rolled, cut, or reshaped. Their electrical characteristics are virtually unchanged during and after bending to 90 degrees. VIMS made with our exemplar recipe do not dry out or warp over time. Thus, VIMS are stable for months when stored under ambient indoor conditions. We charged and discharged VIMS over 100 cycles across 3 months with no noticeable change in performance, which is in line with what we would expect from supercapacitors. VIMS can be combined with other novel, degradable electronics to create systems that are decomposable in backyard conditions in their entirety. Fashion is a domain that is fitting for fully decomposable interactive interfaces. Notably, some accessories are only appropriate to don in certain occasional situations. With this in mind, we developed a very low-power, 100% decomposable on-skin display. Operationally, the system is a 2-state electrochromic display whose transformation is triggered by the application of a lotion, cream, or other electrolytic gel. The display comprises a paper tape substrate with a single layer of PEDOT-PSS, a common conductive polymer that is non-cytotoxic and becomes biodegradable in the presence of hydrogen peroxide, which is widely available and environmentally friendly. The PEDOT ink is highly conductive and electrochromic, serving as both an electrode and an active electrochromic layer. When lotion is applied, free ions migrate towards the electrodes and cause redox reactions. PEDOT becomes noticeably darker under reduction, leading to color changes in the design that saturate in a couple of seconds. The on-skin display is quasi-bistable and can hold its color-changed state for over 10 minutes or until the lotion is wiped off or absorbed by the skin. A chain of 4 VIMS, which can be mounted onto the skin as a bracelet, holds more than enough charge to power this wearable over the course of a whole day with multiple lotion applications. VIMS may also be used in future edible experiences. By definition, eating is an experience that is ephemeral and thus potentially another domain for which VIMS are ideal. Our exemplar VIM design may be made fully edible by replacing the graphite current collectors with edible gold foil, enabling new sustainable interactions during the experience of eating. This is a plot of the current of an edible VIM when shorted through a 47 kilo ohm resistor, which approximates the resistance of a human tongue. Based on characterizations from existing research, the delivered amount of current may be perceived as mildly salty or sour. Edible VIMS may be disguised as decorative gold flakes on food to deliver a tantalizing surprise to the eater. We might imagine yet other applications, such as augmenting or restoring eating experiences for people with taste dysfunction, powering digestible electronics for internal health monitoring, and allowing for programmable flavors to supplement VR experiences. Finally, at end of life, VIMS easily degrade under backyard non-industrial conditions in just a few months. Over the course of 60 days, a VIM we buried in a garden visibly degraded. Only 30% of the VIMS mass remained after those 60 days. Plants near the burial site appear to remain healthy. This is unsurprising since we intentionally selected components that are known to be decomposable. In fact, our exemplar VIMS may be beneficial additions for garden soil health. Many ingredients in our system, including activated charcoal, graphite, and glycerin, are known soil conditioners. Especially with the DIY-friendly nature of our methods, we hope that more makers and designers can prototype with VIMS and discover more recipes, aesthetic possibilities, and applications for VIMS. Thank you for watching, and please reach out to us if you have any questions.